Hi, welcome to the video named Page 40, which is going to cover, just basically talk about building the RSA scheme. In other words, how we get all the numbers to do the RSA encryption, and then we're going to do a big example, which should be very helpful. Okay, so we're going to explain now how, but not necessarily why it works, but we're going to explain how to create an RSA scheme. So the first step is to come up with two large prime numbers. So come up with primes P and Q. And the only reason they're large is because if they're not large, it's easy to break the scheme. Okay, and later we'll talk about how to find prime numbers. Is one of the things we're going to prove in order to prove that our RSA scheme works. We're going to prove that if we're going to find a way that usually gives checks for prime numbers that we will use. Okay, then step 2 is to set the special public number n equal to p times q. Of course, we don't tell people what p and q are separately, we just tell them what n is. So the whole point is the safety is from, you can't factor in. So if someone tries to find out how n can be expressed as a product of prime numbers, it just would take way too long. Okay, then things get really strange, and only when we prove that these things work will we understand why, will we see why. So we make a number of phi, we compute phi, which is p minus 1 times q minus 1. And you absolutely don't publish that. So the only thing being published so far is n. Okay, now in step 4 is to get a number e for exponent, not the natural number, not a log base e kind of e. And so this, we get an e such that the GCD of phi and e is equal to 1, but also equal to s times phi plus d times e. And the number that we're calling d now, this was t when we were talking about the GCD a little while ago. Okay, so and we can assume that d is positive. And that takes a little trick when you're doing the extended Euclidean algorithm to start it the right way. But back on embedded exercise 27, we should have talked about that, or you should have done it. Okay, so that's it. That's the whole scheme. So to encrypt a message A, we compute a number C, which is equal to A to the E in Z sub n. So the computation modular exponentiation gives us A to the E, always reduced mod n, and then transmit it. So we send C out in public. Oh, I forgot to say the E is also public. Oops. So N and E are the things that we publicly tell everyone in the world. And then if someone wants to send a message to us, encrypted message to us, like their credit card number, they can just do this. So they know A, they know the A, they know E, and they know N, and they compute it. And then to decrypt C, you compute C to the D in Z sub n, and we'll prove later that this is equal to A. Yay, so that's cool. Okay, so now we're going to do embedded exercise EEX 28. It's going to take some effort, but it should be good. Okay, So it's embedded exercise 28 says to go through the whole construction with P and Q and send a message and decrypt it. So to do this, we're going to keep the numbers pretty small, and just to make a point, but we don't want them so small that it's ridiculous. So I'm going to pick P equal to, okay, what's a good prime number? I'm going to try 37, and Q equal to, how about 79? Are those both prime numbers? I hope so. Let's see. The old school way of finding out if a number is prime number is to try factors. I'm going to see if anybody divides. 2, 3, 5, 7, 11. Okay, no. 2, nope. 3, and nope. 5, no. 7, no. 11, no. So it's prime because 11 squared is 121, so it's bigger than 79, so we're good. All right, so n is therefore 37 times 79, which I'm now going to turn to my calculator and figure out is in fact 37 times 79 is equal to 2923. So you can see that if someone, this encryption we're going to do, if someone could factor that and come up with P and Q, then they would break our code. It's based entirely. Okay, there's a little, someone was at my door. So, where were we? Oh yeah, so that's n. And the next step is to compute phi, which is P minus 1 times Q minus 1. So that's going to be 36 times 78, which is equal to 36 times 78, 2808. Okay, and we absolutely don't publish that. So we publish to the world n equals and e equals, but that's it. Okay, now we have to construct the code. So we're going to just kind of guess an e. So there's probably some people who really do this have arts and ways to come up with E, but and P and Q for that matter, but I don't know what they are. But let's just take E equal to, the only thing, it can't have a factor in common with 2808, so I'm just going to wing it and say 19. Okay, so then we do the extended GCD. I think I'll have space here. So we're going to do the extended GCD of phi and E. Okay, so let's do that. So we make our normal chart: A, B, Q, R, S, and what we now call D. Okay, so we got 2808. 19. Okay, so 28. So we get divide 2808 divided by 19 is 147 for the quotient point. We subtract 147 and multiply by 19. So that's 15 is the remainder. Okay, so then we promote 1Q becomes A. So no, that's completely wrong. And what we promote B. Whoa, this is going to finish really fast, so it's kind of a bad example. So we promote B to be the A, and R becomes the B, and when it obviously goes in once with a remainder of 4. Then we promote to 15 and 4. 4 goes in 3 times with remainder of, that's 3 times 4 is 12 with remainder of 3. And we promote 4 and 3, and 3 goes into 4 once with the remainder of 1. Then we get 3, 1, 3, 1 goes into 3 times with the remainder of 0, and we promote to 1 and 0, so we're done. Okay, now moving over here. So it did take quite a few steps, despite whittling it down a lot at the beginning. Okay, so now we have to think really hard. So if we use 1 and 0, will it work? And what do I mean by that? What I mean is we've seen this alternating sign here. So if we use 1 and 0, this would become so that's positive, negative, positive, negative, positive, negative, which is what we want. So let's try this. If it doesn't work, we'll have to do it over, which is rather irritating. Okay. So the rule said that S on one stage is the previous guy, and then this is 1 minus the 0 times Q, which is 3. But anyway, it's 1. So let's see, positive, negative, positive, negative, positive. Okay, I think it's going to work. Okay, so the 1 goes over here, and then this is 0 minus 1 times 1, so that's minus 1. And I should be checking these. So is 1 times 4 is 4, plus negative 1 times 3, so that checks. Okay, and this becomes minus 1, and this becomes 1 minus minus 1 times 3, which is 4. The check is minus 1 times 15 is minus 15, plus 4 times 4 is 16. So that adds up to 1. And then we put up cross the 4 over, and this becomes minus 1 minus 4 times 1. So that's minus 5. So 4 times 19 is, I think, 76, and 5 times 15 is 75. So that checks out. And finally we get minus 5. This is the only one we really have to check. And then it's 4 minus minus 5 times 15. So that's 79. Oh my gosh. So 79 is the magic number. So we came up with the extended GCD is equal to 1, because we ended up with 1 and 0. And that is actually equal to minus 5 times 2808 plus 19. Oops, I'm going to do it in the right order. I don't know why this is so small. Okay, plus 79 times 19. And I'm going to check that on my calculator momentarily. So 5 times 2808 is 14040. So this is minus 14040. And the 79 times 19 is, oh my gosh. So I did something, oh, that's horribly wrong. What happened there? Plus 75 plus 4 is 79. Did I type that in wrong? 79 times 19. Nope, that's 1501. Wow. This is terrible. May have to scrap this whole video. Let me cheat a little bit and go back here into the code section in the RSA folder on the course website, and I'm going to run GCD. And it asks me for the larger of the two numbers, so I put in 2808, and the smaller of the two numbers is 19. Oh my gosh. So everything looks good, but then the D seems to be horribly wrong. Oh, you idiot. Do you know what I did? So let me erase. What the heck? What is going on here? Huh. Oh, I want the eraser. I don't understand why this sucker is so small. It seems like a terribly wrong thing. I'll worry about that some other time. Okay, what did I do here? This is very stupid, and I always tend to do it. This one is supposed to be 4 minus minus 5 times not 15, but 147. I often confuse the Q column, which is the one you use when you're computing the D's. So this number is going to be harder to figure. So it's 5 times 147 is 735, so it's 739. And so that's the magic D, which is really horrible, as you'll see shortly. So the, what the heck? So 739. So now on the calculator, 739 times 19 is 14,041. So it does work out. Okay, so all of that work was to find the number D, which is 739. Okay, this is taking forever. Okay, now what do we do? So now we need a message. Actually, we didn't need a message, and we didn't need to get D now, but we could have. So let's just take 123. We can actually take anything smaller than N for the message, for things to work out. Okay, so I need to compute 123 to the, just a moment. Okay, so we're going to compute 123, that's A to the E. E was 19, and we're using Z sub 2923. Okay, so I could do my normal chart and everything, but I'm just going to ask you to do that. I'm going to just run my code. So I'm just going to call run Java on the program modexp. And it wants to know A, so I put in 123. It wants to know E, so I put in 19. It wants N, so I put in 2923. And the answer finally is 234. And we call that C. Okay, so we send C off. 234 is published on the website, and everybody in the world can see it. But back at headquarters, we compute 234 to the D, and Z sub 2923, and this gives us, again, I'm going to use the same modular exponentiation algorithm, and we put in 234 for A, and E is 739, and N is still 2923, and the answer is 123. Yay. Okay, so I did all the steps of the GCD, extended GCD, to show you that, and I didn't do the modular exponentiation, but other than that, that's a complete example of building and using the RSA scheme. And again, if you just handed someone in public N equals 2923 and E equals 19, they could break it by factoring. But as far as anyone on our human planet, human species knows that's talking about it, that would take too long. Of course, it would not take any time hardly at all to factor this, but for a real situation, it could take, until the sun goes supernova. If N is like 300 or 1,000 digits or whatever it takes to beat the computing technology of the time. So that's the end of this little video. Thanks.